Okay, these are the lecture problems for chapters 10 and 11. Take a second to read it. The key to solving these problems is to realize that all of the motion is going to occur about the center of mass. That's what really separates this chapter 10 problem from the chapter 9 problem. The center of mass for the ring is going to be in the center of it. You'd expect the center of mass for the donut to be just inside of it, the same for the ring. And we know that this object is going to go down. It's going to have some velocity at the end of the day. We know what that velocity is. And we're asked to find what this distance is right here. So we can solve this guy by conservation of energy. We're going to say that the potential energy beforehand plus the kinetic energy beforehand is going to be equal to the potential energy afterwards plus the kinetic energy afterwards. If I define my system such that my starting position, my y0, is going to be 0, and my y value right here is going to be negative d, then I can say that my initial potential energy is going to be 0, and this guy was released from rest, so initial kinetic energy is going to be 0. My finishing kinetic energy is going to be negative because I'm below where I started. It's going to be mass times gravity times the distance that I dropped. And the kinetic energy is going to have two forms. We're going to have kinetic energy in the form of translational motion, so kinetic energy about the center of mass. That's going to be 1/2 mass velocity of the center of mass squared. And we're also going to have rotational kinetic energy, which is going to be 1/2 I omega squared. So let me first solve for the easy one. The kinetic energy of the center of mass is going to be equal to 1/2 mass velocity squared. I know that the mass is 4.75 kilograms, and I know that it's going to be traveling at 6.66 meters per second, so I square that guy. I'm going to come up with 105.3 joules. Now to write the rotational kinetic energy, that's going to be 1/2 I omega squared. So what I first need to do is I need to solve for I. I know that I can look this guy up. I for a disk is going to, or a disk with two radiuses, or an open hole disk I should say, is going to be 1/2 mass of the disk, and then the sum of the radiuses squared, r a squared plus r b squared. So here I'll say that the outer radius is going to be radius A, the inner radius is going to be radius B. So I can go ahead and I can calculate this out now. 1/2 the mass is going to be 4.75 kilograms. So this is going to be 0.2 squared plus 0.35 squared. And keep in mind that I've converted the radiuses from centimeters to meters. So I'm going to come out with a rotational mass of 0.386 kilograms meters squared. And I also need to know the angular velocity, but fortunately I know that the angular velocity is simply going to be the velocity divided by the radius, or 6.6 divided by the radius, and this is going to be the outer radius, so that's going to be 0.35. We're using the outer radius because that's the one that the string is attached to, and we're going to come up with 19 radians per second. So now it's a simple matter of saying 1/2, my I is 0.386 6 kilograms meters squared. And then my angular velocity is going to be 19 squared. I peck all that into my calculator and I come up with 69.88 joules. So now I can finally go back up to my starting equation, which says 0 is equal to the potential energy plus the, here I'm going to write these two guys out, kinetic energy of the center of mass, and then the rotational kinetic energy. So I'm going to say 0 is equal to negative mass times gravity times distance plus kcm and kr. So I can add distance, or mass times gravity times distance, to both sides, and then divide by mass times gravity to say that the sum of the kinetic energies about the center of mass and about the, or for rotational, divide that guy by mass and gravity. Plug all these guys in, and I'm going to get 105.3 plus 69.88. Both of these guys are in joules. The mass is 4.75. Gravity is 9.8. And I'm going to come up with my final distance being 3.76 meters. So for part B, we're asked if we dropped that cylinder, that distance, 3.76 meters that we found in the previous part, if we just straight up dropped it without any string, then how fast would it be going? Recalling our energy equation from the previous part, we're going to have now U2 plus K2. However, now there is no string, so we're only going to have KCM being K2. We're not going to have any rotation associated with that. So we're going to say negative U2 is going to be equal to KCM, or negative mass times gravity times negative distance, which is what we used before, is all going to be 1/2 mass velocity squared. We go ahead and we cancel the masses out. Those two negatives become positives. We can multiply both sides by 2 and come up with a square root. So velocity is going to be equal to 2g d square root, or 2 times 9.8 times 3.76. So the final velocity is going to be 8.58 meters per second. So this is faster than if I didn't have that string attached. The reason for that, so part C, the reason for that is because some of the energy goes into rotating the ring if I have the string attached. So not all of the energy can be transformed into velocity as it was able to in part B. So in problem number 1117, this is an equilibrium problem. We know for equilibrium problems we can first draw the free body diagram and then write Newton's second law, set that equal to 0, and solve for what we're interested in. So here we have a dog. My dog is a board because I'm not an artist, and it is being supported by the two scales. We're going to have the force from the rear scale, and we're going to have a force from the front scale supporting the dog. In the downwards direction, we're going to have some weight of the dog, and what we're really interested in is we want to know where that weight is occurring at. It's going to occur at some distance that we don't know. That distance is going to be x. However, we do know the length of our dog. We know that her rear feet are 0.95 meters behind her front feet, so we know how long the dog is. We're just looking for this position X. I know what these forces are. I know that the rear force is going to be 89 newtons and the front force is going to be 157 newtons. So what I want to do is first I want to figure out what her weight is going to be. So I do Newton's second law. Sum of forces in the y direction must be equal to 0. This dog is in equilibrium. It's not accelerating. So we're going to have the rear feet upwards plus the front feet, or the front force upwards, and then the weight in the downwards direction. Obviously you can kind of see that the weight is going to be equal to the sum of those two forces, so 89 plus 157, and we're going to know that the weight of this dog is going to be 246 newtons. Now in order to solve for that position right there, I can use this sum of torques for the dog. The dog is again in equilibrium. All of the torques about this dog are going to be equal to 0. So I'm going to go ahead and I'm going to calculate these torques. I'm just going to pick the rear of the dog. No reason in particular. I could pick the rear or the front with equal ease. So I'm going to say what are my forces and what are my perpendicular distances. So I'm going to have the force of the front feet multiplied by the length of the dog. The force is perpendicular to the length of the dog. And I'm going to, that's in the counterclockwise direction, so that's negative. And then I'm going to have this this weight force, which is going to occur at some distance that I don't know. That distance is going to be x. I'm solving for x, so x is going to be equal to the force of the front feet divided by, or multiplied by the length of the dog, and divide that simply by the weight of the dog. I know that the weight of the dog, or the force of the front feet is going to be 157 newtons, and it's going to occur at 0.95 meters. I use what I solved up here for the weight of the dog, 246 newtons, and I'm going to come up with a position relative to the rear of the dog of 0.606 meters. This you could also give me 0.34 meters from the front feet. Either is an acceptable answer. Okay, so here we have a monkey hanging from a rod, and we're asked to solve for the tension in the two ropes and the angle theta over here on the second rope over here. So I'm going to first start by drawing my free body diagram. I'm going to say I am going to have some tension over here. I'll call that tension number 2. I know that my monkey is applying some weight downwards. It's going to be its mass times gravity. I know that it's also 90 newtons. They've given me that weight. I know that the rod is going to have some weight, and it tells me that it's uniform, so that weight's going to act in the center here. So it tells me I've got 240 newtons acting downwards. That's going to be my force, my weight of the rod. And lastly, I'm going to have some tension from the first rope over here. So I'm going to go ahead and I'm going to break my tensions up into their two components. Do that in red here. So tension 1 in the y direction and tension 1 in the x direction. And here I'm going to have tension 2 in the y direction and tension 2 in the x direction. The reason why I'm doing that is because I'm going to be writing torques, which is going to be the force multiplied by the lever arm, but I know that I can also write this as the perpendicular force multiplied by the distance, and in this particular case it's just easier for me conceptually to write the perpendicular forces and solve for them rather than do the lever arms. And I know that this guy is in equilibrium, so let me first say I'm going to say what are all of the torques, and I'm going to do these torques about my point number 2. The reason why I'm choosing that is because I don't know what tension 2 is, so if I solve for this problem about right there, then my distance between tension 2 and the pivot point, that's 0, so my tension 2 in the y direction is going to go away. Treating clockwise as negative and counterclockwise as positive, as always, I'm going to first have my 90 Newton howler monkey being my force, and that howler monkey is going to be at 0.5 meters. It is giving me a counterclockwise, so a positive torque. Then I'm going to have my weight, my 240 newtons, that's going to be my force. The distance for that is, I know it acts in the center of the rod, and the rod is 3 meters long, so it's going to act at 1.5 meters. And lastly, I have my tension 1 in the y direction. That is going to create a clockwise torque, so it's going to be negative, so tension 1 in the y direction is going to occur at 3 meters. I also know that this angle right here is 150, so that angle is going to be 30. So I could instead write tension 1 as the y direction to be tension 1 multiplied by sine of 30 multiplied by 3, and all this is going to stay the same. I now simply go ahead and I solve this guy for tension 1. So tension 1 is going to be 90 times 1/2, 0.5, plus 240 multiplied by 1.5. Divide that guy by 3 sine of 30, and we're going to get tension 1 to be equal to 270 newtons. Now what I can do is I can say I'm going to write Newton's second law in the x direction, so the force is in the x direction. These guys must be equal to 0. So here I'm going to have tension, I'll say tension 2 in the x direction, it's the positive direction, minus tension 1 in the x direction. I could also say that this is going to be tension 2 cosine of that angle that I don't know, minus tension 1 multiplied by cosine of 30. So I take tension 2, I add this quantity to both sides, and I take 270 and I multiply it by cosine of 30, and I get tension 2 cosine of theta must be equal to 234 newtons. Now I say, okay, what is the sum of the forces in the y direction? Objects in equilibrium must also be equal to 0. So here I have tension 1 in the y direction, and I've got minus the 240 newtons from the weight of the board, and I've got 90 newtons in the downwards direction, and I have tension 2 multiplied by, or tension 2 also in the y direction. And I can very similarly say that this is going to be tension 1 multiplied by the sine of 30. Still got my 240 and my 90, and here I have tension 2 sine of the angle I don't know. So I take my 270 newtons, plug that in right here. All of this stuff is of course equal to 0. So I subtract those, get everything on one side, and I'm left with tension 2 sine of the angle that I don't know must be equal to 195 newtons. So the last thing that I do is I take my two equations here, and I have two unknowns, and I can go ahead and I can solve these two equations for the unknown quantities. Suppose I took those two and I divided them. I'm going to take 1, I'm going to divide that by 2. So I'm going to say tension 2 sine the angle I don't know divided by tension 1 cosine the angle that I don't know. That's going to be 195 newtons divided by 234 newtons. So that tells me that, so what I can do then is, it's going to be tension 2, so what I can do then is cancel those two guys out. I know that this is going to be, the tangent of the theta is going to be 0.833. Take the inverse tangent of both sides, and I'm going to get an angle of 40 degrees. Now it's a simple matter to simply take either equation you want. I'll just take equation 1 for simplicity and say tension 2 must be equal to 195 divided by sine of the angle. It's going to be sine of 40. And now I've solved for tension 2, which is going to be 303 newtons. So at the end of the day, I've calculated both my tensions and my angle using all of Newton's laws for equilibrium.